This here is part 2 in the Trelis Robotics series, and I'll be talking about the main models that we can train to run robots like this. Now, this is a 4-part series. I recommend you check out the first one where I talk about whether you should build or buy robots like this, and I go through the models at a high level. In parts 3 and 4, which will be after this, I'm going to show you how to generate data so you can train the ACT model, one of the models we'll describe today. And in the 4th part, I'll describe how you can fine-tune GR00T N1 from NVIDIA. I'm going to start off today by talking about how robotics models work. It'll be a little bit of a recap on the first video, but I'll add more depth. Then I'm going to show you a demo of some of what I consider the 3 key challenges: modeling in real time, handling delays, and then style or modality issues. That third one is very key. Then I'll go through each of the main model classes: ACT, Action Chunk and Transformer, the GR00T model, Pi0, and I'll talk about some advanced notes then on each of them. So how do models work for robots? Well, they take in a few inputs: a text command, for example, move a blue block into this orange container, a wrist camera image. So here we do have a wrist camera image. Then we have an overhead or a front camera. And we also feed in the current motor positions. That's the positions of the 4 motors here within the follower arm. These are all encoded and fed to a neural net, a transformer, and this predicts a chunk of future motor positions. It's called a chunk because it predicts not just the next motor position, but probably a series of maybe 10, maybe spaced out by 20 milliseconds if the controller is operating at 50 hertz. So here we have it on the robot, and I'll show you by first putting this into teleoperation. By the way, all of the scripts for training, they will be available on trelis.com/advanced-robotics. You can purchase access to this repo here. So I'm just going to start up teleoperation here. I need to make sure that my virtual environment is up and running. And I'll be going into this in much more detail once we get into video 3. I just need to activate virtual environment before I can start teleoperating. And teleoperating will now give me the ability to move my leader arm and control the follower. So here I was just about to show you there are 6 motors. These positions are all fed into the model, and that's true for all the 3 models we'll cover today. There's the wrist camera here, and then there's the front camera here. So those pieces of information are all being fed in. And what we're going to get out is, for each of the motors, we're going to get out a series of probably roughly 10 timestamps. And then the robot will move according to those 10 timestamps if we're in test time mode, not in data creation mode like I am now. And after it's moved those chunks, we will by then hopefully have recomputed the next 10 chunks, and so we'll keep following those chunks as we go. So that's how this model works. And there are 3, well, let me just give a quick example numerically. For example, if we had a 1 motor robot, of course here it's 6, but perhaps the current motor position might be 30 degrees, and the next prediction would be 31 degrees in 20 milliseconds, then 32, then 35, and you'd have 10 of these chunks. The robot will then execute those, so it will, the PID controller will try to achieve those motor positions. And by the time 200 milliseconds have elapsed, which would be the time for 10, 20 millisecond chunks, we would have hopefully computed the next chunk, and so the robot can continue to roll out. And there's a key question around how many time steps you should take, because if you take very many, then the path might diverge from reality owing to dirt or noise. But if you take too few, just predicting 1 or 2 ahead means you may not have a lot of nice continuity between those steps, and perhaps it would be a little bit more jumpy. So what I want to discuss before I go into describing each of the 3 models is a general, I want to give you a general appreciation of some of the challenges here in using robots with AI as opposed to, say, language models. And the first challenge is one of operating in real time, because you need to be able to create future motor positions. You need to predict those, not just for 1 motor, but for all of the motors. And you need to do it very fast because often the controllers operate at, say, 50 hertz. So you need to be generating at least every 20 milliseconds the predicted motor position. And this is why, as I said already in this video, instead of just decoding out one position, we typically decode out multiple, and that's why it's called chunk. The models also are small because we need to keep up with real time. So the largest models we'll be looking at are about 2 to 3 billion parameters compared to maybe hundreds of billions of parameters for large language models. And the smallest model, the ACT model we look at today, has only got maybe a few 100 million parameters. It's about 200 megabytes in size. And that's so that you can do inference fast and so you can keep up with real time. The second thing to appreciate here is that when we are making predictions, we are doing it solely conditioned on the input images and on the input motor positions. We are not feeding in a history of motor positions. So that's unlike text language models where we feed in a sentence and continue it. We are just looking at one timestamp. And because we're looking at one timestamp, it means we can't just capture a delay. If we have the robot delaying here for 6 seconds, it can only see the current camera positions and motor positions. So there's no concept of time delay. Now, if something is happening in the frame, if it can see, for example, this is falling over, it can wait till it falls over because it sees it has fallen over and then maybe it picks it up. But it can't just arbitrarily wait like this unless you change the architecture or the tokens so that you tell it, oh, we have some indication that you should wait for a certain number of seconds. Now, the last thing I want to describe is this concept of multi-modality. And this is not what I thought it was, which is multimodal, image plus text. No, this is a question of styles. And I'll show you exactly what I mean by styles and modes. And this is mathematical modes, as in different kind of solutions to the same problem. So one good example here is navigating around an obstacle. If I have this ball here and the robot comes up to it, it can reasonably navigate around here and get outside it. Or from the same starting position like this, it can reasonably navigate around this side. Now, in both cases, the starting position and the ending position are the same. What's different is just my choice of going left or right. But the problem with simple models, or relatively simple, like the active chunking transformer, is it will make a prediction of a motor position, which is a scalar, like minus 180 to plus 180. And it is going to just average across what it sees. So if it sees me go right once and it sees me go left once, there's this risk where on average, it's just going to bump into that goal. When you just predict a single scalar, you're not able to capture a distribution. And this runs into that collapse issue, which is remedied in different ways by the ACT approach and by the diffusion transformer approach that's taken in Groot and is taken in Pi0. So I've got a slide here I'll just show you quickly on that. You have a starting point. You can take path 1, which is maybe 30-degree angle with the motor as a target. Path 2 might be 10, but because the model just ends up averaging, you end up crashing into the obstacle here. Now, the solution to that is instead of having a conditional autoencoder, and it's conditional because it's conditioned on the current images and motor positions, you introduce a conditional variational autoencoder. And the idea is you need some way to be able to tell the model when it hits this position, oh, you're going to do the left style, or oh, you're going to do the right style. And the way we train it to know which style is by feeding in, this sounds like cheating, but feeding in the actual decoder positions. So by feeding it in the actual trajectory, it's able to learn which trajectory is a left style. I mean, it's all in abstract space, but it's able to distinguish between the styles. And so now we have kind of a map where we have one encoder that will just encode the style, and it will feed that in to the second encoder, which will encode both the style, but also the images and the motor positions. And this can kind of whisper to the main model, the main encoder decoder, to go right or to go left. And at test time, we will represent this. Well, we represent it at train time 2 using this variable z. I've put it as variable v, but it's actually variable z. It should be in this code here. Let me just fix that. At test time, when we're rolling out, we're just going to set that to 0. And that means it's going to just take a fixed style. We don't know if it'll be left or right. If you looked at the data, if you rolled out all the left ones and measured z and averaged that, you could input that z and it would give you a left style. We don't know really a priori whether z equals 0 is left or right, but the important thing is it will be one distinct style. And so long as it's one distinct style, then the model won't just collapse and give an average that results in bumping into things. And you can see this also in a more elaborate example where I could have this style here of picking up the block like this, but I could also have this style of picking up the block like this, where I'm at a 90-degree angle. And I'm being clumsy here now, but if you did train it on being able to pick up in both of those ways, it's just going to average them, and it's going to result in you trying to pick it up, or the model trying to pick it up at a 45-degree angle, which is definitely a bad angle to pick it up at. So that's the idea of the conditional variational autoencoder. And we can see it pretty clearly if we look up the model here, which is the ACT model. Let's just zoom in a little bit. Here we have the CAE, no variation. If you just look at the images coming in, they're encoded. You have the joint positions. If you ignored Z, this would be encoding the input information, positions and images, passing that then to a decoder, which takes in sinusoidal embeddings. There are going to be 10 of these, which are just initialized to a sinusoid, and they then do cross attention. So they will be the queries. These will be the keys and values, and they will be transformed into predictions of the next motor positions. So if you have 10 inputs, they'll be projected into 10 outputs. This without the Z would just be a conditional autoencoder, but we want some whisperer to say, oh, go to the left or go to the right. And that's the Z variable here, which is used and is non-zero during training. In fact, it comes from looking at the action sequence. So we train a separate encoder that gets used to providing a Z to indicate what style is and whispering in here to the bigger encoder so that we can then know what style and not just blend styles during the forward pass. Now, as I mentioned, at inference time, we just set this to 0, which is going to choose either left or right. We don't know which, but importantly, it will just choose one, so it won't result in collapse. Now, when we train this end to end, we are also going to train this encoder here to get Z, and we are going to weight the loss here. Now, the more we weight the loss here in the transformer encoder, the less the entire network will want to stash information in here. So we want to weight it sufficiently so that it doesn't stash any other information about the movement. So we don't want it to stash general picking up information in this encoder and Z, but we do want it to stash style information. So that's where tuning of beta comes into play. If we have beta too high, it won't stash any information, so it won't be able to whisper the style effectively. But if we make it too small, then it's going to stash information that really should have been stashed in the encoder and decoder and is necessary for replicating the experiment. So that's the ACT transformer. And there are variations of this. The first one is bi-ACT, which basically finds that if you predict not just motor positions, but torques and angles, then you get the benefit of improved dexterity. And it kind of makes sense because this here, for example, is squeezy. But the way I know that it's squeezy is because I am able to feel the torque. Here, if I'm just predicting motor positions, there's no real way to convey how tightly to squeeze this. It's kind of conveyed via the position here of the leader arm, but not as delicately as if we had torque as well. So this is one nice takeaway. I think it's an improvement, potentially could be brought to Groot and Pi0 as well later on. Then there's multi-ACT, which allows us to train an ACT model, which is quite simple, but on multiple tasks. Unfortunately, if you try to train ACT on different tasks, it will just average across them. If you try to put in a specific token at the start for each task, it still ends up averaging across them, which maybe wasn't obvious to me, but that's a problem. So to get around that, if you look at the multi-ACT paper, the authors go to quite a bit of effort in order to build a classifier. And what they do is they will detect which task it is. For example, maybe there's a task of pushing to the left or pushing to the right. And what it will do is it will see, oh, we're kind of to the left of this cube, so maybe it's a pushing to the right task. And further, it will activate certain weights for that task. So this is kind of involved. And the reason it's involved is because of this problem that with continuous variable predictions, we don't have a way to map the shape of all of the modes or all of the styles that are possible. Now, before I go on to Groot, just a few final notes on ACT. Why not use tokens? Well, if you use tokens, then instead of having a continuous motor prediction, which would be averaged maybe to the wrong value, you would have a distribution, and it can be bimodal. So you might have a distribution of 2 angles that represent 2 different styles, or maybe 4 angles if there were 4 ways to pick up that cube. But now you need to have tokens. You need to quantize your motors. It's nice already to have this continuity. If you create bins, you need many bins to make it smooth. You then need a softmax to be able to calculate the probabilities across for each motor. So you add compute as well. Why not use auto regression? We are, instead of decoding one time step at a time, we're doing all of them. This is primarily for a matter of speed. It ends up being a bit too slow if you only decode one at a time. It's a bit like audio models. The information is quite rich. There's a lot to decode. And so it's more efficient to just decode out more. Otherwise, it's hard to keep up with real time. Why not use action histories? I mentioned how you can feed in, or you do feed in the images and the motor positions, but not the histories. Turns out if you do pass in a little bit of the history, it helps stabilize quite a lot. It's not covered in the GR00T or the Pi0 paper, but that's the improvement that probably could be brought. Last of all, and this is quite subtle, but the transformer that decodes out actions or motor positions in ACT, it will use key or queries to look in cross-attention at the information coming from the encoders. We can take a quick look again here, how we are going to have cross-attention. So the queries are these position embeddings. The keys and values are going to be the information from the encoder. But actually, these embeddings do not look at each other. So the first value of motor position, that's not providing any direct influence to the second value. So you can have more discontinuity between those 10 predictions. And if you had allowed for bidirectional attention there, self-attention, you may get a smoother profile. It's an idea that's used in Pi0. Next, we're going to chat about GR00T N1. And there are 2 issues I want to cover. First is that it's a diffusion model, so is Pi0. This gets around the style or multi-modal issue that we talked about earlier, and it allows it to cover many tasks in the same model. Second of all, GR00T is trained on unlabeled data, videos of robots, without knowing the motor angles. Now, when we gather data sets, which we might do, say like this, using a leader to basically record data sets, we definitely know the motor positions here. We've got the images, but we've also got the motor positions. What I'm saying is GR00T is trained just on images. So how do you link that to motor positions? That's what I want to describe. But first, just a little bit on diffusion models and how they avoid this multimodal issue. You see, a diffusion model starts with noise. And the idea is to start off with noise and remove the noise, to clean it into a vector. That's a vector that represents a direction in which to move. Well, you want to find a direction that removes the noise in such a way that you end up with motor positions, because ultimately we're trying to predict motor positions. But the key thing is we are trying to find the direction in this high dimensional space to remove noise. And because we're finding a direction rather than just finding this scalar value, that ends up avoiding the averaging that was happening in the ACT case. And here's kind of loosely how I think about it. If we have a starting point, we have a path now that we're trying to find, and we have a path here. Both of these paths will avoid the obstacle. But when we sample, and we sample that noise initially, basically we will end up on kind of one side of this hill or the other. So you can think of it as a 3-dimensional surface. Maybe here in the middle, there's an obstacle, but the local minimum here is on the left. The local minimum here is on the right. And if we start off slightly to the left, we will move down there. If we start off slightly to the right, we will move down here. But we are mapping the full surface with diffusion. And because we're mapping the full surface, we're able to represent all of these different directions, and we're able to represent essentially the different modes that are present, not just kind of the average. And this is the key advantage of the diffusion model over just predicting a single continuous variable. So here, the first starting point, we go that way. Second one, we go this way. And the diffusion model essentially allows us to map a surface so we can record multiple styles. This brings us to the second question, which is, well, if we have this video data, how is it that we're able to use it to train the model? Because we ultimately kind of need to have motor positions. And the answer is by using these abstract latents, which you can think of as representing movements to new motor positions, but not in the context of a specific robot like this, but in a more abstract sense that could be applicable to many robots. And here's how that's done. Think first of all of a video. Maybe you could record a video of this arm or this one here, and you've got a time equals 0 position on your video, and you have a time equals 1 position. And the idea to get these abstract representations of that movement is to take those two time stamps, this one time equals 0 and 1, and pass them to an encoder whose job is to create that latent, which is a vector representing the movement. And the way we check that it's the right movement description is we ask a decoder, a different neural net, to take that latent, combine it with the t equals 1 position, and reproduce combine it with the t equals 0 position and reproduce the t equals 1 position. And if that's possible and accurate, it means we now have a description in latent space, in abstract space, of this movement from position 0 to position 1. And if we have that, the latent description, and we have the videos as inputs, what we can do is we can train our GR00T model on these videos, and we can back propagate using this action latent as a label. And that's exactly what GR00T does. So GR00T involves taking image, text, like the instruction, the command, and the motor positions, passing them to a diffusion transformer, and trying to get the diffusion transformer to diffuse out an action latent for which we do have labels. Now, there's one more step you need to put this into practice, which is that action latent would need to be made applicable to this set of motors, but that can be done quite easily through just a small set of weights and some quick fine-tuning, maybe a multi-layer perceptron, maybe a linear layer, and that will bring you out to some motor positions. So essentially what GR00T is saying is, well, we can't train for these final motor positions because we don't have those, but what we can do is we can use this encoder-decoder setup to create some action latents and use them to back propagate through the diffusion transformer here. So this is the concept of GR00T. I'm going to quickly describe Pi0 because then I'll show you the papers. There are quite a few similarities. Pi0 though is trained on label data, as I understand, not action latents. Pi0 uses bidirectional sense attention when decoding. This is more of an advanced comment, but when we're decoding, say 10 time steps, it allows queries to be made between those 10 time steps for improved continuity, which I understand is not present in GR00T. Pi0 uses layer-wise attention. This is quite analogous to the progression of vision language models like edifix. Originally, the idea would be to take vision information, encoded vision information, and do what's called cross-attention with something you want to decode. So you want to decode out positions, you start with some sinusoidal embeddings, and then you do cross-attention with these sinusoidal embeddings as the queries, and these as the keys and values. And these keys and values might come in at every single layer across ways, and then you decode out. But there's some kind of duplication because you're passing these in, the same information you're passing in at multiple layers. Whereas the approach of Pi0 is, much like the later edifix models, you move to passing everything in at the start, and you do attention on a layer-wise basis. So information goes in at the bottom, regardless of the modality, vision or text, or motors, and you cross-attend here at every, you self-attend at every layer here, rather than repeat the same attention, the same cross-attention at every layer, which just introduces the same information multiple times. So yeah, it turns out this way here of doing it, of feeding upwards, ends up being a bit more efficient or gives better performance. And so probably not surprising that this is maybe the direction Pi0 took. Now, Pi0 also uses a diffusion type approach. So they diffuse out an action latent. So in that sense, it's quite similar to what's being done in the NVIDIA GR00T example. Now, before I describe which model to use, I want to just cover each of those papers very quickly. Let's take a look at GR00T. There's a nice diagram down here, actually. Let's just find it. Actually, this one here is good. So what we can see is the images are coming in. They're going through an encoder. The embeddings then are correctly sized to feed into Eagle 2, which is a vision language model. The text is tokenized and fed in as well. And then this information is fed in multiple times. You can see it's literally repeated because it's cross-attention. And it's mixed in with information from the state encoder, which is the motor positions, the current motor positions, but also the noisy predicted motor positions. So the idea is you start off with noisy predicted motor positions for the future, maybe 10 steps. You do self-attention between them and the current motor states. You do cross-attention with the vision and text information, and you hopefully remove some noise. Then you loop back around, move more noise, and you do this 4 times in this model here before you hopefully end up then with your motor predictions. So this is NVIDIA GR00T right here. And you can see, well, it's not exactly obvious from this diagram, but when you're going to train on the latents, you will have this multi-layer perceptron afterwards, effectively, that will need to be fine-tuned, but you will be training on the latents that are coming out of this cross-attention and action decoder setup here. Lastly, let me just show you quickly the Pi0. So here, again, we have these vision transformers to encode to the right dimensions. This is polygemma. It's using a SIG-LIP for encoding the images and then combining that with Gemma, a 2.6B model, so about 3 billion parameters in total. And then we're taking in the text info, then we're taking in the motor positions, and then we're taking in the noise, and that's again going to loop through multiple times and have noise removed at each step. Notice here, well, you can't actually see it, but this is set up to be causal between blocks. So this forward pass here does not see any information from the noise, but the noise does see and attend to information from all of the past stages. The motor actions do not see the noise, but they see everything before it. So it's causal on a block by block basis. Importantly, here, what's called the action expert is a different set of weights. So the transformer weights here, the Gemma weights, they are different to the weights that are used here in doing the diffusion transformer. So a different set of weights. And there is cross-attention between, or self-attention, in fact, is the right term, between the noise and the motor positions and the information over here. But the weights are going to be different. So these are not being initiated from the VLM. They're being trained from scratch in this case here. So this is Pi0. And yeah, as I mentioned, the key difference is, I believe a lot of the pre-training here, it's using labeled data and a fairly large corpus of labeled data. So with that, you've got the question of what model to use, because I'm going to cover training ACT and then cover fine-tuning GR00T in the next videos. ACT is a small model. It's fast. It works well on edge devices, but it's quite limited to only a single task, mostly because of these issues around style and modality. GR00T or Pi0 are larger, they're slower, but they're more general. They may work without any fine-tuning, or if not, you might do a small amount of fine-tuning and they'll work well. Just a few advanced notes then to finish off on GR00T or Pi0. Something we talked about earlier is adding torque predictions. Currently, these models are just doing position predictions, but adding torque, that ability to squeeze, particularly for objects that, are a little bit squeezable here, that could improve the dexterity. Adding a short motor position history, I mentioned how these models all take the current snapshots of images and motor positions. Adding in a little history, even one motor position, can improve stability quite a lot. I didn't talk about ensembling, but when we predict chunks in the future, you don't have to wait. You don't have to have them with zero overlap. You could actually start creating chunks such that they overlap, and you can kind of exponentially average across those overlapping chunks. That can improve stability, and does for ACT in some cases, but the Pi0 paper reports that it's worse. So that's kind of interesting. Probably it depends on the hyperparameters. And last of all, speed is critical if you want to run real time. That's a reason for going towards smaller models. Then you do have these trade-offs around handling multiple modalities or multiple use cases, which probably is important in a lot of cases if you want to be quite robust. So that's it for the 3 main models. I will go through them a bit more when we train them. I'll be training next up the ACT model and then GR00T N1, and the scripts for that will be in the Trelis Advanced Robotics repo. You can go to trelis.com, trelis1l.com/advanced-robotics. And I may add some extra videos afterwards. That is a paid repo, but throughout these videos, I'll try and describe in detail so you can try to find the information yourself and maybe develop it with the help of ChatGPT. In the meantime, let me know if you have any questions and put them down below in the comments. Cheers, folks.